So based on last class, I think I got just enough time to keep a pretty good pace. So we're gonna hit all of these. First question, there's a couple of blocks. There's M1, M2, there's a spring, and this thing is gonna fall delta Y, and that delta Y is the maximum stretch distance, which is different from the equilibrium. Remember, it overshoots the equilibrium and then kind of oscillate back and forth initially. Okay, so they tell you what those are. Okay, we know all that. That diagram is pretty self-explanatory. Okay. Block 2 starts from rev, speeds up. Right now, why does block 2 initially speed up as it's falling, but then slow down? First, explain it only in terms of forces, because I see this diagram, I immediately think conservation of energy, which we're going to have to do here in a minute anyway. Okay. But in terms of forces, when you say that if you did a free body diagram on the skating block, its weight is initially more than the tension force, which has something to do with the spring. But as it falls, it stretches the spring more and more, and eventually the force from the spring is more than the weight of the block. And when that happens, then go through the tension string. There's going to be a net upward force on this block, which would therefore slow it down. Okay, so they were probably looking for something like that. However, they scored that. Derive an expression for the distance delta y that block 2 travels before momentarily coming to rest. Express your answer in terms of all those variables and any physical constant. Now this one, here's your conservation of energy. So this is for a closed system. This would be the block, or block or blocks spring earth system. And it goes like this. Sum of energy initial equals sum of energy final. And I could call it a closed system like this because friction is negligible. Okay? And the initial energy, isn't that all from block 2 falling? So I'm going to say mass 2 g delta y, because delta y is the fall distance, right? Okay. And then when it falls down there, I'll call it potential energy 0 at that location. Okay. And where's that energy go? Well, it goes into the spring. There's your 1/2 kx squared, 1/2 k. But instead of x, shouldn't I say delta y? Yeah. Do you guys notice that the fall distance and the spring stretch is the exact same value, right? Okay. What about kinetic energy? Do you have to account for that? Oh, shoot. Now I'm thinking. Oh no, we're good. I think. Right? Yeah. Okay. Because there is kinetic between point A and point B, but not at this point. I was thinking for a moment. Wait a minute. There's no friction, but okay. No, we're good because that counts for the spring. So this is the entire setup. Right. So one of these cancels. Yeah. Thanks for checking me too. Right. I think we're solving for delta y, right? Times 2 over k. So we got 2 m2g on k. There you go. Hey, the more the hanging block weighs, the more it's going to stretch. The more the spring constant, the less it stretches. Hey, kind of makes sense, right? There's your answer. All right, what else we got? Indicate whether the total mechanical energy of the block's spring earth system changes as it moves downward. Remember, friction is negligible. Therefore, is energy conserved? Yeah, it does not change. Right? Briefly explain your reasoning. Hopefully you said, now they've got a rubric on their end. I'm going to make some guesses what might be in that rubric for points. Maybe something about a closed system, maybe something about friction being negligible. Well, anything else I'm maybe missing? I think those are probably 2 pretty important points, right? Okay, then there's this third part. So we're looking at initial and final energy with negligible friction, which has been the premise all along. And they're saying, but what if there was friction? What if friction was not negligible? Ooh, there is friction. What would the after picture look like? Now, they only have 2 types of energy. They have energy in the spring and gravitational potential. All right. So if there is friction, and this is an open system, and they said the surface of the table is not included in the system, so we're looking at an open system. Shouldn't there be less overall energy after compared to before? Yeah. Right. So I'm thinking one good answer might be 0 gravitational potential, and then spring energy that's less than this bar. Yeah. All right. I think also if you had a little bit of gravitational potential, as long as these 2 added up to less than the initial bar, then you should get full credit. Okay. Right. Okay, I think that covers that one. Does that cover that one? All right, you guys good there? All right, you guys knocking out all these points. Ooh, I'm feeling lots of 5s. Yeah. The moons. All right, let's get the answer to the moons. We got 2 moons. They said identical, so same mass is probably the most important factor. And there are these distances from the planet center to center distances, but maybe they're kind of ambiguous. Maybe we don't know exactly what the ratio is, or right, but we know moon A is further away. Okay. On these dots, draw the free body diagrams for these moons. All right. So for moon A versus moon B, okay. For moon A, did you guys have that there's a force from moon B?
Yeah,
and a force from the planet. Yeah. If you use a straight edge, then even better. Right?
I know I did that too.
Oh, right. And moon B, yeah, there's
Both on the planet
planet and moon A. There you go. Just like that. You guys got that?
Yeah.
But a couple of points. Right. Oh, this was a 12 pointer. So I'm gonna guess that's worth 2 points, but who knows? Okay. Consider the net gravitational force exerted on each moon. Justify why the magnitude of the net force on moon A could be larger than that of B. Okay, so I think this is pretty open-ended. There's probably lots of possible correct answers, but I'm going to give you maybe pretty straightforward one, right? All right. Guys, is it possible that moon B, all the gravitational force might cancel out and zero out?
Yeah.
I would have said that, because if that happens, there would definitely be a net force on A, which therefore the magnitude has to be greater than zero, right? That would be an easy possible answer for why, right? Not the only answer, but could be. Justify why the opposite might be true. How could you have a net force on B greater than that on A? Now this one's a little trickier, but how about this? What if moon B was very close to the planet, moon A was very, very far away? Yeah, I see a lot of you guys nodding. Because then what that would do is it make this force huge. And it would make each of these forces really tiny, including this one. So these three really tiny, this one huge, right? If you spread out these like this, right? Okay. All right. That'd probably be the most straightforward way to solve that. Derive expressions for the quantities, the net force on moon A, the net force on moon B, in terms of mass and constant, the whole deal. All right, let's try this out. What is the net? I'm gonna run out of paper. Okay. Let's start over here. Okay. So remember, A has force from moon B and also the planet.
Yeah.
Okay, and then moon B, well, they're just pulling opposite directions, right? Force from moon A and force from the planet. Okay, and these FPs are different. Okay, so I'm just all right. Okay, so the net force on moon A is well, those two added together, right? So it'd be G. Did say M naught was the mass of the moon, right? M naught mass planet. I guess we do this one first. Divided by RA squared, right? RA squared. I want landscape and everything to not run out of room, but I'm gonna run out of room. So because that's a plus, right? G M naught, and you could have said M naught squared. That would have been fine too. Right. Now, would this have been the difference between these two?
Yeah.
Right. Yeah, exactly. RA minus RB squared. Okay. So sorry, I got kind of a broken line solution there. Oops. But that would be so the net force is this plus this, right? How about F net on moon B? Okay, so get this diagram out. Okay, so the planet's definitely pulling to the right. So universal gravity constant, mass of the moon, mass of the planet, whatever order you do that. RB squared, yeah. I don't know why I still do this. It's weird. In my mind, I can't distinguish between capital and lowercase r. I don't know. It's weird. R. And then subtract. Yeah. G. M. Moon. M moon. You could say M moon squared. Yeah. The difference squared. There you go. All right. All right. You guys probably got that? Okay. All right. Doing good. Doing good. Could
you just justify?
Right. Yeah. Justify. So do these equations justify the possibilities before? So the answer to each of these questions is going to be yes, and then you just poke around the equations and say like why these could match up to the stories that you said before, right? Okay, so I think if you guys get this far, you can get that right. Next one, the hanging block in the wheel. All right, so they explain it here, but it's pretty self-explanatory from the picture what's going on, right? Guys, we did a lab that's almost exactly this. You guys remember breaking out the PVC pipe and wanting to string around the central axle, and there's a block hanging down, and it rotated faster. We did a whole tau equals I times alpha graph with it. Yeah, so we pretty much did this. Well, this is an experimental design too. Okay, so design an experimental procedure. Students are going to compare an increase in the block's translational kinetic energy with the decrease in gravitational potential innate energy of the block Earth system as the block falls. Oh, whoops, I think I forgot to read something. Sorry. Let me hit this part. There's two students talking to each other. One student says the kinetic energy in the block increases as it falls. Is that true? Yeah. Kinetic energy is increasing as it falls, going faster, faster. Right? Second student says that this is because the gravitational potential energy is converged to kinetic energy. Is that also true? Yeah, isn't it losing potential and gaining kinetic? That's also true. Now, so I'm thinking that both students are correct, but there is another part of the story. Here, let me fill in the rest of the story, which I think is going to come back in later. I'm going to do energy conservation, right? And say that the hanging block falling was supplying all the energy. And it went into speeding up that block, 1/2 mv squared. But it also, where else did the energy go? Exactly, rotating that wheel. Wouldn't that also be true? Right, and this V and this omega are connected, but that's your basic setup, right? Oh yeah, go ahead. Right, guys got that? Okay, so this kind of come back pretty soon, but let's check out what we're supposed to do here. You guys got to design an experiment. Two tests. Okay, we're comparing the block's increase in kinetic energy to its decrease in gravitational potential energy. Now, obviously, those are not going to equate because they're forgetting about this. But there's a way to measure it to test that. And they're going to find out, right? So, what are we measuring, and how are we measuring it? Right, so, did you guys say you're going to use measure mass with a scale or a balance? You guys said something like that. Now you're allowed to know G is 10 meters per second squared. Okay. Did you guys say you're going to use a meter stick to measure the height?
Yes.
Right. Okay. Now the speed, I can think of two ways to do it with different tools. What did you guys say? Motion detector, that's the most straightforward way. Guys, most straightforward way is to just stick a motion detector right down here and directly measure the speed as it's falling. Right. Now there's sort of a trickier roundabout way you could have done this too. Right. And it goes back to something that I told you guys about before. Okay. It's like this. If you're looking at speed as a function of time. Okay. Speed is a function of time. Okay. Now it starts from rest, right? So at time 0 to 0 speed. Do you think it's gonna it's probably going to accelerate uniformly, I'm thinking. Just I'm thinking about that. I think that'd be correct, right? Something like that. Right. Well, as long as it has uniform acceleration, the next part would be true. Okay. Whatever speed it is at, I could call that V final. Wouldn't that be true? Right. And that'd be actually what you were interested in on the table. Right. You can calculate that sort of a roundabout way by getting the average speed, V bar, from the total height fall divided by the total time. Okay, so if you did distance over time with a meter stick and a stopwatch and found the average speed of falling, then you just take that and double it. So this is 2 times V bar. Okay, we've done this before a couple of times. So it's a little tricky step, but you can solve it that way. Okay, so there you go. There's 2 different methods you could use to solve the speed. But again, if you did a motion detector, it's probably the most straightforward way. Right. Okay, and I guess you could say like use this tool to measure this thing, blah 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 blah. Right. Explain how they could determine kinetic energy of the block immediately before it hits the floor. Yeah, right. So there you go. Just 1/2 mv squared. Yeah. So some version of that, right? Okay. All right. Now we're looking at kinetic energy gained by the block and then lost gravitational potential energy lost by the block. See how there's more energy gravitational potential energy lost and kinetic energy gain. But that's exactly what I would have predicted because this right here. Remember, students have been forgetting about this right here. But that's where this is going to come in because on the graph, draw a line or curve to represent the rotational kinetic energy of the wheel as a function of the falling distance d. Now, if this is a closed system, the block, wheel, earth system, and there's negligible friction, then shouldn't the total change in energy be 0? Right? So if you're drawing a third line, I would draw a straight line, probably about like this,
Yeah.
so that at any particular point, they add up to a total of, well, so add up to 0. Okay. For example, at 20 centimeters falling distance, negative 0.4 here, what adds up to 0.4? Well, this is less than 0.2, so I need something more than 0.2. That's probably right about here. I put a point right there, align it with 0, 0. That's the answer. Okay, you guys can do that? And you did that. All right, all right. I'm feeling some vibes. Students also measure angular velocity, omega, as it falls, and the kinetic energy, rotational kinetic energy of the wheel. So if you're talking about this omega and this rotational kinetic energy, right? And then they plot rotational kinetic as a function of omega squared. Hey, should these points line up in a linear graph, straight line? They should. In fact, it says that. It says draw a straight line that best represents the data. They're helping you out, straight line. Right? So here's kinetic energy, rotational kinetic energy. Here's your omega squared. They're treating as the x-axis. Is 1/2 I equal to the slope? Do you guys see that? 1/2 I is the slope, right? So using that line you just drew, create experimental, calculate experimental value for rotational inertia of the wheel. All you do is take the slope and multiply it by 2. That's it. Take this slope, multiply by 2. That gives you I. Yeah. We've done that a number of times in this class, including a bunch of labs, including one of the very first labs you guys ever did. You guys remember the Hot Wheels cars rolling down the ramp, right? And x was 1/2 a t squared, right? So the slope was 1/2 a on an x versus t squared graph, right? Which you guys graphed. Yeah. So yeah, that's exactly in line with what we've been doing all year. Right? Number 4. Should tell you guys what. Yeah, let's do this one. A student has a piece of clay and a rubber sphere, same mass, so identical mass, so that's controlled for. Throw it horizontally, same speed, identical blocks as shown. So friction is negligible. After the collisions, both blocks fall to the floor. Right? In case A, the clay sticks. In case B, the rubber sphere boing bounces off. Wouldn't that be called inelastic and elastic? Right? Right? Okay. So we're looking at momentum of the clay block system after the collision for case A, right? And now they're saying, what is it for case B? Now, guys, if everything was identical except for the coefficient of restitution, okay, guys. Shouldn't there be the same momentum in the system, mass times velocity? And isn't momentum conserved for the system? So shouldn't this look exactly like this? Yeah, exactly the same, isn't it? Yeah, you guys got that? All you had to do is take this and copy paste it right here, right?
Yeah.
Right. Now remember that's for the entire system. We're talking about the sphere block system, right? Now, if you look at the sphere and block individually, okay, well that's where it gets a little trickier. But for the whole system, yeah, it's exactly the same. Right. I think it's what we're supposed to do. Yeah. So that's all that there was to that one. Part B. After the clay in block A collide, block A lands distance dA from the edge of the table. So goes and some distance like down here. Okay. Does block B land further from the table or not as far? What did you guys say for block B? Further, exactly, because it's elastic. So it's sent off with a greater speed, right? Yeah, greater. Hold on, greater impulse on the block.
Yeah.
True. Yeah, the block does land further. You guys said further, right? Because boing. Yeah, and that is something exactly that we've talked about a few times in this class too. So yeah, all right. As long as you guys were present that day or those several days that we talked about that, then you're good to go. And last one. The math's on the spring. Sorry, but I'll take you guys over the answer. Yeah. All right, so we got mass, spring, 1 meter above a motion detector. They told you what the mass is, but we don't know what the spring constant is. We don't know how stiff that spring is, right? Then what we're gonna do is let this thing down to equilibrium, then pull a few more centimeters and let it oscillate back and forth. And they give you height versus time. Now this height refers to height above the motion detector. You guys see 60 centimeters looks like the equilibrium point that it's oscillating about, right? Now guys, if it's oscillating about 60 centimeters, then how much was the spring actually stretched to equilibrium? Got 1 meter, take away the 60, what are you left with? 40, right? Do you guys see this? The stretch amount would actually be 40 centimeters, right? Right. So using that info from the graph, calculate the spring constant. I will show you guys 2 different ways to calculate spring. Actually, you know what? I think I've got the notes marked up here already. I do. I've got 2 different methods, and I'll show you guys both of them right here. Okay. So one method is you could have said, well, at the equilibrium point, it would have been hanging out right here at the 60 centimeters above motion detector, which really means 40 centimeters of stretch, right? So 3-by diagram. So I'm using a force method. The weight down and the spring force up balance out, right? And then you know 3 of the square values because they told you the mass of the block. You're allowed to know G, and you know you can kind of figure out the stretch amount is 40 centimeters. Call it 0.4 meters. Solve for K. K is 12.5 Newton per meter. Okay, that's one way to do it. There's another way you could have done. Could you guys have used that spring oscillation formula? That period of oscillation. Guys, what's the time period of oscillation? You guys see 1.25 seconds? You guys see 1.25 seconds for 1 cycle?
Yes.
Right? Do you guys remember this one right here from unit 6? Right? And you have this and you have this. Plug in 1.25 seconds, plug in 0.5 kilograms, solve for K. Oh, you get almost exactly the same thing. Look at that. Right? You guys see that? It's like the same thing. All right. So yeah, and I'm sure you could have done either of those and got credit. All right. At time 0.75 seconds, the object spring Earth system has total kinetic energy K naught and total potential energy U naught. Oh, I should say this too. I mentioned this a few times in this class. When it says total potential energy, they're talking about the sum of both gravitational potential and also spring potential. Okay, yeah, all right, you guys remember that? That was a little tricky, but right. At time 1.13 seconds, right here, again, total kinetic energy K naught, total potential energy U naught. Ooh, so you're saying the mix of energies is the same. Up here would be well, I wouldn't say the spring is compressed, but it's more, it's not stretched enough to reach equilibrium. And here it's overstretched from equilibrium, right? Right. And they're saying it's the same mix of energies, right? Now why? Well, so we're getting these questions. Explain how a feature of the graph that indicates total kinetic energy of the system is the same. Kinetic energy, that's your 1/2 mv squared, right? So if the m is the same and the v is the same, that would be one way to do it, right? Right now the m is obviously the same, it's the same mass. What about v? Guys, what property of this graph tells you something about velocity? Distance versus time. The slope. Let's check out the slope. We're checking out the slope at 0.75 seconds. Hold my ruler right here. There's those here. There's the slope of the tangent line there, right? How about down here at 1.13 seconds? Hey, it's the same slope. You guys see the tangent line at the same slope? That means it's the same speed. That means you pop into 1/2 mv squared, and you're going to get the exact same kinetic energy, right? You guys got that? Where's my? Okay, you guys good? There might be another explanation they would have accepted too, but that's what I would have gone with. I think that's my best guess as to how they would have scored that. Okay. Briefly explain why the total potential energy of the system is also the same at these 2 times. Right. So I think the most straightforward way to say that because it's a closed system and the total energy is the same and the kinetic energy is the same, if you take the total energy, you subtract the equivalent kinetic energy, the potential, the leftover potential energy, both types also has to be the same. Okay.
I also had both times. They have the same displacement.
Okay. Yeah, I think you could have gone about that way too. The fact that they're the same distance from the equilibrium position.
Yeah.
Let me think about that. Yeah, I think you could have taken that route and gone about that. I think that would have been probably a lot more math, a lot trickier. But yeah, I think you could have done that. Or if this was a multi-part question, it's possible that maybe if you mentioned that detail, could have gotten a point out of that maybe. So, yeah. Yeah, there's probably different ways to do that, but I would have said total energy is the same, closed system, subtract the kinetic energy, which is also the same to both. Therefore, spring potential plus gravitational potential must also be the same at both points. Okay. All right. Experiments repeated with a 4 times the spring constant. See how they quadrupled the spring constant? And I think everything else is the same. Determine the new equilibrium position above the motion detector. All right, where's my work on this? Hold on. There we go. Here we go. Okay. Okay. So here's our dynamics, right? Our forces framework, guys. If mass is the same and g is the same, all this is the same. Right? If you quadruple the k, what has to happen to the x to balance everything out? 1/4. Yeah. So the stretch amount was 1/4 of what it used to be. Now remember, before the stretch amount was 40 centimeters or 0.4 meters, right? Now that you sort of had to figure out because 1 meter minus 60 centimeters is 40 centimeters, right? Right. So 1/4 of 40 centimeters would be like 10 centimeters, wouldn't it? Okay, but then there's one last bit you have to do. If the equilibrium stretch position is only 10 centimeters, then what would the height above that detector have actually been? If this stretch is only by 10 centimeters, what's the height? 90 centimeters, right? And I think if you got everything exactly right, that's exactly what they would have looked for, is 90 centimeters for full credit. Okay, 90 centimeters. Okay, and then last part for this will close it out right here. The object again, pull down distance d naught, which we know from before was 5 centimeters, right? You guys remember 5 centimeters, right? And then release. So basically, make the graph. What's this look like? Right? So we got a real stiff spring this time, right? Guys, the fact that we got a real stiff spring, the spring constant is 4 times what it was before. What does that do to the time period?
No, 1/2.
Half the time period. You guys see that? If factor of 4 on that k, you got half the time period. Okay, so let's put this all together because we got all the components flying around. So the time period used to be 1.25 seconds. Now it's going to be half of that. So, right. So, and then at the equilibrium mark, I'm going to put 90 centimeters. We're pulling it down 5, so this would be down to 85, and it would go up to 95, wouldn't it? So if you guys go 85, 90, 95, right? And then one full cycle would be half of what this was, which was right here. Let's go, probably look something like that. Okay, or you could put 2 full cycles in 1.25 seconds. You go here, okay, look at that, and they give you one more graph just for scratch work. All right, there it is. There's the answers to all of your FRQs. Yeah, I hope you guys feel pretty good about those because that is it. What are we doing now? We're doing. Oh, well, you guys got rest of class to say what you need to study or do or play with those circle law calculators, which are fun. Or you can work on paper roller coasters if you like. And tomorrow's plan is to take those bottle rockets and go outside and blast some rockets. Oh yeah.